Okay, so this will be about reaction mechanisms and how to deduce the rate equation from the mechanisms. Okay, so for the purpose of this, let's have a reaction. Okay, let's say x, wait, okay, let's say x plus y becomes z. And let's use an analogy here. Let's say there's this like water tap. Okay, so there's a tap over here, and there is a reservoir. Okay, this reservoir is made of the reactants x and y. Okay, and somehow when it goes through the tap, a reaction happens, right? So it flows out as z. So in this analogy, the rate at which the water flows out is the rate at which the products are formed. Okay, so we know that in a single step reaction, that means that x and y just collide together and form z. There's no funny mechanism, there are no intermediate products or anything. Okay, and in this single step reaction, we know that the rate equation, okay, tells us that the rate, okay, is dependent on the rate constant, the concentration of x, and the concentration of y, which are the concentration of the reactants here, right? So that is if it's a single step mechanism. Okay, but we know that not all the time x plus y may not always combine to form z, right? They may have x plus y form 2x first or something. Okay, so an example here is given by this. Okay, so we have a mechanism here. Okay, this is a lecture notes example. The mechanism is not that NO2 plus CO will just combine and then they form NO and CO2, right? They have two steps. NO2 will combine with itself first to form NO3 and NO, and NO3 plus CO combines with CO2 plus NO2. So in this case, what actually happens, right? We know that step 1, it can be modeled as like this little tap here. And in this reservoir, it's kind of like NO2 plus NO2, right? And after that, the products flow out. Okay, whatever flows out, it goes through a second step, right? Okay, and then it flows out here. Okay, so this is what the products from step 1 is the reactants for step 2. This is the products for step 2, and the overall reaction, the overall equation is like this, right? And so we put in some reactants here, in this case NO2 and CO. We put in all the reactants here, and whatever flows out are the products through this two-step reaction. So what's the difference between this and this and a single step? We both have reactants poured in, okay, and we both have products from out, right? The difference is really in the rate at which the products flowed out. What do I mean? Okay, let me give an example. Suppose that is a two-step reaction. Yeah, I'll just draw a very exaggerated. Okay. So we can model it kind of like this, right? Okay. So whatever we put in here, you realize that the tap can only allow this amount to flow out, right? So if you just imagine like having this kind of a tap system, it doesn't matter how big or how big this part can be, as long as it's bigger than the slowest part. Okay, as long as it's bigger than the smallest tap, no matter what, the whole tap, okay, the whole equation will give me the flow, okay, the flow that the products flow out of the whole equation is only dependent on this, right? It doesn't matter even if it's a three-step reaction. Okay, yeah, it doesn't matter even if there are 3 steps. Okay, if there's another step here that flows like this, or even if there's a step before it, okay, no matter what, whatever flows out of the whole equation will be this, right? So this is kind of like the restricting thing for the rate. Okay, it's kind of like the restricting tap, and this is the slowest thing. Okay, it allows water to flow out the slowest, so it's called the slow step. Or because the whole rate of this whole equation, the rate of flow of water that comes out of this whole system is only dependent, or is exactly the same as the rate at which it flows out of the smallest step or the narrowest step, right? So this is also known as the rate determining step, because the whole equation is only determined by this step, right? Because yeah, I can have another water tank over here that comes out, and even though it can flow out as much here, right, it flows out a lot here, the moment it comes here it will get restricted and it flows like this. Okay, so if this is the rate determining step, we know that, suppose that this is x and y, okay, and this x and y becomes z, or whatever product, z plus a or whatever, then the rate at which this tap, okay, occurs, or the rate at which this tap allows the water to flow out, is given by rate equals to k of x and y. And so it doesn't matter what, maybe this rate, okay, at which the water flows out could be rate equals to k of z cube. Okay, it doesn't matter. What matters is that this is the rate determining step. So even if this can be kz cube, can have other kinds of rates, the whole equation, okay, or the whole reaction will have this rate of flow similar to the rate of flow of this step. So I don't really care about this part. Okay, so this is the rate determining step, and this rate is the rate of the whole equation. So if I go back to my previous example over here, we have NO2 plus NO2, and we know that this rate, okay, the rate at which this flows out here, is given by rate equals to k NO2 NO2, or NO2 squared, right? And the rate at which this one flows out here is given by rate equals to k, okay, because of the products, right? At step 3 is NO3 and CO, NO3 CO. But does it really matter? No, because no matter what, the whole reaction is only given by this, right? So whatever flows out is dependent on this rate, so is rate k NO2 NO2, and so the whole overall reaction, okay, has a rate equation, rate equals to k NO2 squared. So this is the intuitive understanding. Just try to visualize this kind of a model, and no matter what, the amount of water that flows out of the whole system is, or the rate at which the water flows out of the whole system is the same as the rate at which the water can flow out from the narrowest one, and that's the slow step. Okay, so that is the intuitive understanding. Now let's give another example. Okay, yeah, rate. Okay, so we know that there are two steps here. NO plus Cl becomes NoCl2, and this is a fast step. Okay, so I'll represent it with very wide tap. Okay, it allows the reaction to go very fast. It allows a lot of water, allows the rate of water to flow out really fast, right? So this is NO and Cl2, and it flows out NoCl2. Okay, and then I have the slow step, which is the narrowest step, right? Doesn't allow a lot of water to flow out. And this is NO plus NoCl2 to give you the 2NoCl. So we know that, of course, this one has a rate equals to KNoCl2. Here, this one, this tab over here gives me rate equals to K NO and NoCl2. And because this is the slow step, okay, because this is the slow step, sorry, I know this is off the screen. Okay, because this is a slow step, we know that the rate of the whole reaction is only this. But you see there's an intermediate here, NoCl2. In the overall equation, or in the reactants here, there is no NO and NoCl2, right? It's just NO and Cl2. So how do we convert this rate? Because the rate equation must be expressed as rate equal to K times something of the reactants, okay, or of the things that are being reacted, and not an intermediate. So how do we try to kind of think of it? The rate here, right, NoCl2, okay, is also the NoCl2 over dt, or the concentration of NoCl2 over time, right, which is K NoCl2. Now if we times time on both sides, we actually get an equation like this, right? NoCl2 equals to K NO Cl2 times time, right? Because the rate NoCl2 over time is K NoCl2. So if we put time on the other side, it's kind of like K times NO, concentration of NO times Cl2 times time. So we know that the concentration of NoCl2 depends on the concentration of NO and on the concentration of Cl2, right? So the formation of NoCl2, the rate at which this is formed in order to react, right, is dependent on NO and Cl2. So we can kind of like substitute it in. If we know that the rate equation is rate equals to K NoCl2 times Cl2, okay, then right from over here, oh sorry, times NO, okay, then we can kind of like substitute this because this is dependent on NO and Cl2 equals to K NO Cl2 times NO, or K NO squared Cl2. Now you must be asking, what about this K, right? What about this T? Okay, in the first place, you have to understand that the K here is different from the K here. Okay, although they may be K, but because they are kind of like different rates, they are sort of different. And at the end of the day, even if you put a K here and you kind of times it together, it's still a constant, right? So it's still a rate constant, although the value may be different, but the rate equation is not so concerned about the value, but more of how the rate is dependent on the concentration of the reactant. Now what about the time here? Okay, of course this one is slightly confusing, but it's more complex than that, okay, because this assumes that it's not being consumed, right? But the moment it comes down to the reservoir over here, every time it comes down and it's being consumed, okay, so just ignore the time for this, for understanding, okay. Just understand that NoCl2 is dependent, okay, on NO times Cl2, okay. It's dependent on this, and so because it's dependent on this intermediate can be replaced with NO and Cl2, and that's how you get the rate equations. Typical questions that will come up for this is to have a mechanism, and they ask you if, you know, from the experimental data you have proposed a certain rate equation, like a second order to NO and first order to Cl2, and after that they tell you which mechanism is explains this, right? So if you understand that, first, okay, the first step is always find the rate determining step, okay, and then after that have the rate in terms of the reactants of the rate determining step, for example xy. Okay, these are the reactants of the rate determining step, reactants of rate determining step. And if x and y are intermediates, then find out, let's suppose x is an intermediate, okay, is an intermediate, then find out what does x, okay, how is x related to, or how is the formation of x, the rate of formation of x related to the reactants. Okay, so if previously you know that a plus b becomes x, right? So x here is kind of the concentration of x is kind of related, okay, or is dependent on concentration of a times concentration of b. Then you replace the intermediates, whatever intermediate it is, with concentration, okay, concentration of b, and that's how you get the rate equation from a mechanism. And then you compare that whether this kind of agrees with the experimental data that you have got, okay.